I will talk today about nonlinear Hall effect in multilayer magnetic topological insulator manganese bismuth telluride, or MnBi2Te4 for short. And this material is quite similar to the bismuth telluride family of topological insulators, but an additional manganese and tellurium layer into the subtopo layers that we get here. This introduction of magnetism moves us from the regular topological insulator band structure to a more unique type of band structure with both band inversion and an exchange gap. And this allows for a range of exotic topological quantum states, one of which being the quantum anomalous Hall effect, which people have found that MnBi2Te has a very high quantization. Additionally, because of this antiferromagnetic ordering, we can actually tune the magnetism by the number of layers in MnBi2Te. So this high quantization case is monolayer, but also 3-layer and 5-layer, because they have an odd number of layers, will have uncompensated magnetism. So you can see that they still have an open loop for this anomalous Hall effect at zero field, whereas this even number of layers, 4 in this case, the magnetization is fully compensated at zero field, and we have a closed loop instead. Recently, about a year ago, 2 papers came out that showcased this nonlinear Hall effect in MnBi2Te, which is measured using second harmonic voltage, which means that voltage is measured at twice the frequency of the input current. And this second harmonic part is the quadratic component of the voltage response, which gives us this quadratic type of IV curve. Both of the papers found that this effect comes from the quantum metric, which in turn is the real part of the quantum geometry. For comparison, the more well-studied and well-known Berry curvature is instead the imaginary part of the quantum geometry. And this requires that both the inversion and time reversal symmetries are broken, which has been achieved in different ways. For example, as shown here with encapsulation of black phosphorus, so that both inversion and time reversal symmetries are broken separately, so that the combined PT symmetry is preserved, which is then required by the quantum metric. Because of this, this nonlinear Hall effect has been limited so far in few layer MnBi2Te below the Néel temperature, where we have this antiferromagnetic domain. In our work, we've been using exfoliated multilayers of MnBi2Te, so a bit thicker than what has previously been reported. And first, we can measure with ARPAS that we can see clearly the bulk bands as well as the topological surface states. And it's not super clear in this image, but we can see an exchange gap in the surface states. So this tells us both that we have excellent crystallinity in our sample and also ferromagnetism in the surface. Then we can take cuts at different energy levels and measure circular dichroism. And here the color isn't exactly spin, but it's somehow related to spins. So we can see that we have some sort of spin polarization in this band structure. Then we can also measure the ordinary Hall effect for different current directions across the crystal. And we find that this 0-degree angle gives a maximum response. And this is also where we pass most of the current in our experiments. Next, we map out the magnetic phase diagram of MnBi2Te. Here we use the DC magnetic resistance, but we can also get very similar results using first harmonic, both Rx and Rxy. But when we do a field sweep like this, we see that we have 2 kinks, and most likely there is some sort of magnetic phase transition between these 2 points. So if we repeat this for several different temperatures, we get different kinks at slightly different positions in field and temperature. And then we can repeat this also for temperature sweeps following this kink for different applied fields. And then we can take the positions of all of these kinks and plot them. And we get these borders between different magnetic phases, which we can then compare to literature to identify that we have this antiferromagnetic phase that's ground state. Then for higher fields, we undergo spin flop transition to a canted antiferromagnetic state. And then for high fields and high temperatures, respectively, we have ferromagnetic and paramagnetic phases. What I would like to emphasize is this nonlinear Hall effect that we're able to measure in these multi-layer devices, which we measure using lock-in amplifiers, in this case at 2 Kelvin and 0 field. And we measure both the longitudinal and the transverse voltage, where of course the transverse voltage is the Hall effect. And as you can see in both of these curves, that we have this characteristic quadratic IV dependence. So if we take a closer look at this Hall effect, we can see that it has a very interesting dependence both on temperature and field, especially here with the temperature sweeps where we have a kink and then a sharp increase in nonlinear Hall resistance. And if we take a look at this kink position for different applied fields, we can see that this corresponds pretty well to the Neal temperature that we can see in our magnetic phase diagram. So when the MBT enters the antiferromagnetic phase, we have a sharply increasing nonlinear Hall effect. We can see similar here in the field sweeps that maximum signal comes at low field and low temperature. Here, however, we don't see a sharp kink because this is in plane field. So most likely instead of like sharp switch, we are slowly pulling the spins towards the in-plane direction. But in both of these experiments, we can see that we have a very strong correlation between the magnetic phase of MBT and the nonlinear Hall effect. So this is still ongoing work, and one of the main open questions is the origin of this nonlinear Hall effect. I've spoken before about the quantum metric, but there are two key differences between this and what has been previously published. First being that since we have multi-layers, we're a bit more bulk-like, which might give us slightly different symmetry situation in our devices, where we might actually have preserved inversion symmetry in the bulk of the crystal as opposed to the thin layer case. And second is that we see very clearly here nonlinear signal even above the Neal temperature, where we should be in the paramagnetic phase. And also here at high fields, we see a small but non-zero signal, even though we are most likely in a quite ferromagnetic phase. And neither of these are expected, at least for the thin layer case, for the quantum metric. So some alternatives might be the more well-known Berry phase or asymmetric Magnon scattering. Both of these have been shown in other topological materials to give rise to similar nonlinear Hall effects. So we're still investigating exactly what is the mechanism behind this nonlinear Hall effect. Finally, I would like to thank my supervisor and colleagues for the contributions to this work, and thank you very much for your attention.
Thank you, Lars, for the talk. Are there any questions? You can either speak if you have a microphone or type them in the chat. I have one initial question regarding your higher harmonic measurements. So your second harmonics, right? You measure. So I think the advantage of thin films is that you can really do the measurement in different crystallographic direction. And if this is a phase from Berry phase, they should give you, if I am, for the knowledge I have, different results. Have you tried to, I don't know, your devices, if you can measure in different crystallographic direction with respect to the sample and see different
Yes, we did similar to this device. We tried measuring also higher harmonics. We haven't been successful so far. We had some issues with the contacts, but this is under fabrication right now. Some new devices tried out. But thank you for the question. It's a good point.
Do we have any other question? Okay, if not, I think we can move on to the